Welcome back, everybody. And the topic this week is to try to wrap up the discussion which we began with last Friday, where we were calculating expectation values. Now, this means that we have to look back into some of the slides from last week, but I will mainly use the whiteboard. Now, the kind of notation which we have introduced till now is something which traditionally is called first quantization. Another way of calling it is actually the coordinate space representation. Now, since we are going to deal with many particles, it's going to be convenient to introduce a new notation. And this is called in many different ways. The name which I prefer is called number occupation, because then instead of keeping track of all the positions of the particles, you keep track of the states which the particles are in. And this gives us a much more compact notation. And this notation introduces some new formalism and some new operators. It's actually a mapping of the states which we have, where we till now have described all degrees of freedom, the spatial degrees of freedom and all other quantum numbers in a given state function. So the formalism which we are going to introduce is normally called second quantization. It gives you the kind of feeling that there are different types of quantization. So this is just some kind of name which has stuck with the formalism. So if I say number representation, or it's also called Fock space representation, these are typical names which I think are more precise. But you will also hear me say second quantization, because that's basically established in the literature. So if you've taken a course in quantum field theory or field theory in general, you have probably encountered the so-called creation and annihilation operators. So you can view this as a transformation of your basis into another basis. So we are going to introduce these operators this week. But first, we are going to wrap up some of the more, tedious calculations. And we will mainly focus on systems of fermions. The biggest complication is actually in calculations of fermionic systems, because we have to take into account a wave function or an ansatz for the wave function, which has to be antisymmetric under the exchange of, let's say, two particles. So the bosonic case leads to a symmetric wave function, which, when we then use a single particle basis as an ansatz for making a many-body state, then the consequence is that a single quantum mechanical state, where you can have a single particle, can actually be occupied by many particles. Whereas in fermionic case, the consequence of the anti-symmetry requirement on the total wave function leads to, within the framework of a single particle basis description, this is an ansatz which we make about the system, that this is a viable approximation to a many particle system. And then we will construct a many-body wave function based on a basis of single particle states. If you're dealing with a strongly interacting system, this kind of approximation normally breaks down, but you can always impose anti-symmetrizations on the total ansatz for the wave function. I'm saying ansatz often simply because we don't have the exact solution to the equations. Because if we had, there's no point for you being here, because then the problem is solved. So everything we deal with is different ansatzes for solving a complicated many-particle problem. And these ansatzes are then baked into mathematical algorithms. And every mathematical algorithm gives rise to one specific type of many-body methods, as we discussed last week. The simplest one is what we call a mean field approach, which commonly is often called Hartree-Fock theory, which also leads to density functional theory, which is the method which is widely used in material science and quantum chemistry for dealing with the many interacting particles. We have full configuration interaction theory, which actually means that we diagonalize a Hamiltonian matrix within a basis. And then we have other approximative methods, because when we have a basis, it means that we have made a truncation. And that truncation is a truncation from an infinite set of states, which is then reduced to an effective Hilbert space. So sometimes we can make precise mathematical mappings from the full Hilbert space to an effective Hilbert space. But in many, many cases, we simply have to proceed with an ad hoc approach where we restrict the number of states, and then we augment the number of states. And if the energy converges to a given limit, which we have defined, then we are happy and we will stop. So full configuration interaction is also diagonalizing a matrix. So it's essentially a Hamiltonian eigenvalue problem. And then we have other methods like many-body perturbation theory, which we will also discuss, which you can view as a Taylor expansion around a specific energy. And then we have other methods which we'll discuss, like copper cluster theory. Monte Carlo methods are actually discussed in another course which runs in the spring. So this leads to stochastic approaches. So I'm just repeating some of the things which we said last week. So what we are going to do now in the first lecture is actually to repeat some of the things which we went through at the end of the lecture last week. And then after that, we are going to introduce a much more compact notation, which is second quantization, which leads to an efficient way of dealing with systems of many particles. And most of the formalism which we will discuss throughout the semester will be based on this approach, second quantization or number representation. The topics which we will also need to introduce in like next week is something which is called Wick's theorem, which also facilitates the calculations of quantum mechanical expectation values and transition probabilities. So has anyone here heard of Wick's theorem? If you've taken a course in quantum field theory, that's pretty common. So if you've taken a course in quantum field theory, you will recognize many of the things which we are going to discuss. Okay, so I'm going to switch back to the whiteboard and basically stay with that for the rest of the day. So let me just bring that up. So what we did last week was to introduce an ansatz for the state function, which for fermions is something which we can, based on a single particle basis, express as a determinant. So a determinant has the properties that if we interchange two columns or two rows, it changes sign. And you can now think of every column representing a specific particle. And that specific particle, if you interchange that with another one, then the determinant changes sign. So that's one way of implementing the Pauli anti-symmetry principle. Okay, so let me just bring it up again. And we had a definition of a Hamiltonian, which we wrote with a H with a hat on top. So I'm trying to be consequent with hats on tops of operators. But if I forget, I hope you can see from the context that this is an operator acting on something. So the Hamiltonian operator is something which we have rewritten in terms of one part which we call H0, which is normally a part which has a physical interpretation. So the system has some properties which can be described by this H0, but it doesn't contain the full part of the Hamiltonian. So there's an I here, which is typically the interaction between two or more particles. So this H0, just to remind you of that one, is, since we're now dealing with all the quantum numbers, so we have a notation where we now start with particle 1 up to particle n. So uppercase letter n stands for the number of particles which we're going to deal with. And then we have an operator which we call a one-body operator, which then acts on one particle at a time. So this is called a one-body. And the typical form of that operator, H0 of x of I, is something which then can contain the kinetic energy of a given particle I. And then we have the Laplacian. So this represents the kinetic energy. And then there can be some external potential, so which we're just going to write as an EXT. It could be a harmonic oscillator which traps it, or any other type of external potential which confines the motion of a particle in one way or the other. Yeah.
Is an XI a role?
No, the XI is what we last time introduced as a collective denominator for the spatial degrees of freedom. So this contains the positions of a given particle in 1, 2, 3 dimensions or higher dimensions. And then it contains also the spin degrees of freedom. So a state, the hope then is actually that this one has a basis, which we labeled as an alpha of j. It doesn't need to be x of I, but multiply with x of I here. That this specific basis is an eigenbasis of that part of the Hamiltonian. Now, this phi is then an eigenbasis of a part of the Hamiltonian, and it's this eigenbasis which we are using as an ansatz for constructing a many-particle wave function. So one of the things which we're going to show today, and which you will also have in the exercises later on, is that you can construct a many-particle basis based on a one-particle basis, which then is an eigenbasis of this operator H0 here. So the state which we had, just to remind you quickly of that, this alpha j, these alpha j's are specific quantum numbers which then could be related to orbital momentum, etc., etc. And we have an x of I here. So this is the tensor product of a state psi alpha j, and where we have only the spatial degrees of freedom, so I'm putting a vector sign here. And this is given by the tensor product with a part here which then contains the spin degrees of freedom. So if we have a spin half object, if sigma I is equal to 1/2, this has two possible projections along a given z-axis, which then takes the values +1/2 or -1/2. And we would often just label that one with a spin up and a spin down. So this is a kind of shorthand notation which we use. So this Hamiltonian which you saw here, this H0 here, does not need to depend on the spin degrees of freedom. So if it doesn't depend on spin degrees of freedom, I mean the spins don't affect the expectation value which you're constructing. The HI part, just to remind you of that one, can be a two-particle interaction, but it can also be a more complicated interaction between 3 or more particles. So in general, we will just stay with an interaction which I'm going to label as an XI, XJ. And we're going to put a label 2 here, but we could have higher order terms, free-body interactions, where we have a V3, XI, XJ, XK, and plus. But we are going to actually approximate everything with just a two-body interaction. This is the most common case you encounter. So if you're coming from condensed matter physics, from atomic physics, molecular physics, quantum chemistry, this is actually the standard approximation. So we are going to skip the subscript 2, but we're simply going to have this XI, XJ. And in general, as we discussed last time, this interaction has some specific symmetries. And it's normally translational invariant, it's permutational invariant, it is rotational invariant, that's another symmetry which it respects. So our XI, XJ is normally a function which is proportional to another function, which I'm going to call V prime, which then depends only on the relative distance between two particles. That's the most common situation. So there is no spin degree of freedom, but you can have that. So if you move to nuclear physics, the nuclear Hamiltonian between protons and neutrons has also spin interaction. And it has some more complicated interaction because it's not symmetric around the RI-RJ. It has actually some actual nuclear systems exhibit deformations, and that has to be accounted for more complicated terms than something which is just centrally symmetric. So in atomic physics, we just have what's called the Coulomb interaction, which depends only on some constants times the inverse of the relative distance. So the most common potential which we are going to encounter is something like, and now I'm just taking away the prime, and I'm just writing this as an Ri. This is just to introduce the kind of notation we will use. This is going to be a function of a variable, which we will typically call Rij. And it's given by some constants, which we call lambda, divided by this Ri minus Rj. And just to remind you quickly, so this Rij is just a shorthand for the relative distance, the absolute value of the relative distance. And if we are in 2 dimensions, this is x1, xi minus xj squared. This is for 2-dimensional case. And then I have a yi minus yj squared. If you have 3 dimensions, you have to add a z, etc., etc. So this is one of the most common types of interactions which we have. Okay, any questions so far? So what we did last time was then to introduce a so-called Slater determinant as an ansatz for the trial wave function. So the Slater determinant is a way to build up an ansatz for the ground state of the system. And we are going to use the letter phi here and 0 for the lowest lying state, the first state, the fundamental state, or just the ground state. And this is going to be a quantity which then will depend on the positions of the different particles up to Rn, will depend on the spins, sigma 2 up to sigma n. And then we can have additional quantum numbers, like an alpha 1 up to some alpha n here. So you will often see me writing this out in a more compact way, like phi 0, and then I will just write 1, 2, up to n here. That is another kind of more compact notation because it gets boring to write down all these quantum numbers, okay? Now, one of the things which we discussed last time is actually to define a so-called transposition operator. So the ansatz which we had, this function here, is then given by a determinant where we now have a normalization factor which reflects all the permutations or transpositions which we can make. And in that specific case, we have for a column, so we start with alpha 1, and then we have x1 here, and then phi alpha 2, x1. So the columns represent the given particles, x1, and then we have a phi alpha 1, x2 here. This goes all the way down to alpha n. So the rows represent the given single particle quantum numbers, whereas the columns represent the particles. Now, this is also set up because the particles are identical and indistinguishable. Now, these are also functions which are orthogonal to each other. So it means that when I calculate the integral of phi alpha I of x, of phi alpha j of x, this is given by delta alpha I alpha j. And this is often written out in the terms alpha I, alpha j in a more compact notation. So that's the norm. So we assume that the basis is orthogonal and normalized. That's a standard approximation which we are going to deal with. Now, the thing which we defined last time in terms of transpositions is that you see now that when you interchange two particles, the Pauli principle requires then that the wave function should change sign. So the thing which we defined last time is the transposition. That's a transposition operator. And then we labeled this one with a, so not to be mixed up with the projection operator we defined last week, but this just transposes particle 1 and 2. So when this one acts on a state like this, and now I'm just taking the liberty of writing it as 1, 2, up to n, and then we have I here and j, and up to n. This is the same as phi of 1, 2, and then we have transposed I and j. And this is the same as minus phi of 1, 2, of I, of j, up to n. So I'm going to state many of these things without giving you proofs. So some of these are just statements about mathematical properties, because every such statement could require some more precise proofs, which easily can lead to at least 1 more hours of lectures. So I'm just going to state many of the properties of specific operators, and then just demonstrate the properties by simple examples. So when we do this permutation, you see that for every permutation, you have a minus sign. So typically, or transposition, what you typically have then is a minus sign every time you do that. And the determinant, we know that the determinant, if you now think of a 2 by 2 determinant, if you just set that one up, A11, A12, A21, just to remind you of that, what we did last week, this is the same as A11 times A22 minus. So there we have a transposition, and then we are interchanging columns 1 and 2. So you will see then that the row is the same, but then we are having now a transposition here of, from this one, from what we call the basic ordering. And we can actually rewrite this one in terms of what we defined last week as the Leibniz representation of a Slater determinant, which is then given by the following expression. So let me just quickly set that up for you. So the Leibniz representation, let me just bring this up here. If I take a determinant like this one, determinant A, this is given by a sum, this sum pi, over all the permutations which we can make. So if we have 3 objects which we permute, then we have 6 permutations. 3 objects is 3 factorial ways to permute. And you see that if you write out a 3 by 3 determinant, you will have 6 terms. And one of these terms correspond to you not doing anything. And then what you will have now is a number of p permutations which are doing. And this is then multiplied with the basic elements. And now I'm setting up a general Slater determinant. I have A1, which is the first row we are looking at. So we are setting this up according to a specific ground ordering. So where you can think of you ordering the Slater determinants with respect to the diagonal, the product of the diagonal elements, and then you permute the different columns. So we are going to write this as a pi of 1. And then we have the next element, which is A2, so the diagonal, and then we permute that one with one of the columns. And this goes all the way, if we have a general determinant, up to this AN, and then I have a pi of n here. So if you think back to the 2 by 2 determinant, you see now that you have 0 permutations, 0 changes, which is actually this guy here. But then you have the next one, and you see now that you have interchanged here 1 with 2 and 2 with 1. So this sign or this symbol which you see here means that I have now taken into account the possibility of interchanging the 2 columns. So this is a more compact notation of the same thing which you see here. If you go back to a 3x3 determinant, as we discussed last time, just let me quickly remind you of that. So if we have a simple 3x3 determinant, A11, A12, A13, and then A21, A22, and A23, and A31, A32. So what we are doing now is simply to use the diagonal elements as our basis for making the permutation. This is actually something which is physically motivated, and you will see that in the next drawing which we make. But in this particular case, what you have now is you would have the sum over all the permutations. So Sn is the set of all possible permutations, transpositions you can make. And then you would now have the change, which you have if you have one permutation, it's minus. If you have two, it's plus again. And then you have the basic element, A1, and then you change the column. And then you have an A2, and you can change the column, multiplied with A3, and then you can change the third column. And if you write this out, as you have seen in most mathematics courses, this would be a typical A11, and then you would have an A22 times an A33 minus an A32 times an A23. That's the first term. So just watching the first, and then you have four more. And I'm just lazy now, so I'm just not going to write out all of them because we did that last week. But you see now that the first term is the one where we have not done anything. So you would call this one for the basic arrangement or the ground arrangement or the initial arrangement. And then you see that the next term which you have contains now A11. So there's nothing done with A11. We don't change the column, the first column. But if you look at the next one, what we have now is that A22 has interchanged 2 with 3, column 2 with 3. And then we have the same thing here with 3 and 2. So this is something which we then would think of as a permutation 1, 3, 2. So this would just be simply our basic ordering, 1, 2, 3. Now, if you then write out all the other elements, you will obviously get something which goes like 3, 2, 1. You will get 2, 1, 3, and 2 more terms. We did that. We wrote this out last week, and we put those labels on it. So this is a more compact way of writing down the determinant, because sometimes it's a little bit boring to write down all these elements. But there is another reason for why we do this. So if you go back to the wave function which you have here, if you now look at the diagonal elements which we have here, there's a reason why we want to use that as a kind of ordering. So if we look at our ansatz for a physical system, you could now think of or go back to the case which we had last week of atomic helium and atomic beryllium. So in atomic helium, as an example, we would have the 1s orbit, which is the lowest lying orbit if we use a hydrogen-like basis. So if you solve the hydrogen system, we know that we have analytical solutions. You can add a charge to that. Instead of having charge equal to 1, you can have a charge equal to 2. This is not the exact solution to atomic helium when you have an interaction, but it is the solution to the non-interacting system. Now, in that specific case, what we did was actually to put in some states, because we are using now the consequence of the Pauli principle, and we label that as a state 1 and 2. And each one of these boxes point to specific quantum numbers. So you could think of this as a pointer, which then computationally points to specific quantum numbers like the spin, it could be the orbital momentum, the number of nodes the wave function has, etc. Then the next one would be a 2s state. There's a slight degeneracy here in atomic hydrogen. These states 2p and 2s are degenerate. But here we would have 2 new slots, so which we now are leaving empty. So we have 3 and 4. Now 2p has a degeneracy of 6, so we can actually fill in 6 electrons. So if we fill in these slots as well with particles, we would have atomic neon, the next noble gas. If you fill in the next shells, and now I'm just putting them on the same level, like a 3s, a 3p, and 3d, I guess this rings a bell, right? So it means that we could now make an ansatz for the ground state of atomic helium. This is an ansatz. So our ansatz phi 0 would then be given by a Slater determinant over 1 over square root of 2, where we then have a phi, and now we are putting a 1 here, which indicates that this is box 1. And then we have particle 1 here, and then we have a phi alpha 2, particle 2, but then it has to be antisymmetric. So then we have an alpha 1 of x2, so we have an interchange here. Like that. So this will be an ansatz for atomic helium. In principle, we have an infinity of states here. So somewhere we are going to make a truncation. And that truncation is something which we labeled with the label D, but D stands for the dimension of the single particle basis. Now, if you look at the ansatz we made, we defined a truncation here, which goes in here. This is something which typically defines in a system of fermions what we call the Fermi level. So this is not the exact solution. However, this state which we have is actually the eigenstate, and we are going to show that today, of phi 0. So this is going to give us an epsilon 0 times phi 0. And that epsilon 0, as we calculated last time, is simply given, so epsilon is an uppercase, it's given by epsilon alpha 1 plus epsilon alpha 2. So that's our first ansatz for the ground state energy of atomic helium. Now we can become more ambitious now, and we could say that let's do atomic neon. Then we would fill in the next box and the next box. And in total, then we have 10 electrons. And then we would have a 10 electron determinant. So that would be a 10 by 10 determinant. Okay? So I'm just repeating some of these things which we went through last time. So the reason why we then want to make a determinant which has a specific base ordering in terms of these states here is simply because we are now picking states like here and here, and we want to use these states in a kind of ascending order where we simply say that 1 is the one with the lowest energy. In this case, we have a degeneracy, so 1 and 2 have the same energy because there is no spin part in the Hamiltonian which can lift the energy, the degeneracy. But in principle, you could think of having 1 here, 2 here, etc. Okay, any questions? I hope it's not too boring because I'm repeating some of the things I did last week. And you can then construct more and more complicated states or with more particles and have these as ansatz for the ground state of the system. So this is one of the starting points. We have to make an ansatz. And based on that ansatz, we can construct, since these single particle states are orthogonal and normally normalized, then we can actually make a many-body state. And this is one of the exercises next week, where you actually show that if the single particle basis is normalized, then if you build a many-body basis on that, that will also be normalized and orthogonal. So that's also an important aspect. Okay, any questions? Okay, so last week what we did then was to calculate the expectation value of atomic helium for that specific Hamiltonian. And you saw all that was a pretty boring exercise. So we had to go through all the arrangements of the wave function. And at the end, you saw probably that if we now go to more particles, let's say 10 particles, this is going to be a tedious, boring exercise. So the question is now whether we can make something which is simpler and simplify the calculations and obtain the expectation value with such a determinant for just a given one with a given number of particles. Now, to do so, we need to introduce a new character in the play here. And this is the anti-symmetrization operator. So if you now look back at this Leibniz representation of a Slater determinant, you can actually rewrite this in terms of a symmetries or what it calls permutation operator, where you simply where we define an operator now, which I'm going to call the anti-symmetrization operator. And this operator is going to be called A, and it's given by all the possible permutation, one of all the possible permutations. And it contains a sum over all the permutations we can make. And then we have this sign, obviously. So if we permute two columns, we have a minus sign. If we do this twice, we get a plus sign, etc., etc. And then I'm going to introduce just an operator P, which now takes into account all the possible permutations which we can have. So this P could then be, if you look back at this example with the 3x3 determinant. So the first one would be this one, so nothing happens. We call this zero permutation. Then we interchange 2 and 3. We can interchange 3, 2, and 1, etc., etc. So this is P is now simply all the possible ways you can make the permutation for n objects. Okay, so it's another way of just writing what we have here in terms of the Leibniz representation of a determinant. So some of you may have seen that. I know that those of you who have taken classical mechanics here, you have seen that way of representing a determinant. And you've probably also seen that in terms of the so-called Levi-Civita symbols. So there are many different ways. There are often many what I call hidden gems in linear algebra, which pop up and are very useful. And sometimes we've never seen any of those because the teachers in linear algebra were interested in other things. Like when I took linear algebra at my university, which is a technical university, the teacher was a pure mathematician and we were all engineering students. And the teacher started the first lecture by saying that matrices and vectors are just something for engineers. And we are going to talk about groups and group theories, etc., etc. Nobody understood anything. So it depends very much on your linear algebra teacher, okay? And this course is actually a course where we often have need many of these kind of small practical gems which you find in linear algebra, which often are not taught in a linear algebra course. Okay, now this operator has a very important property. It's idempotent. So it acts like a projection operator. So this A squared is equal to A. So let me just show you a quick demonstration. If we have two particles or two objects, then this A becomes A of 2, and that is equal to 1/2, because we have 2 factorial. Then we have 1, so we are not doing any permutations. And then we have minus P12. So P12 corresponds to exactly what you saw here in this specific case, where we now interchange column 2 and 1. So this is just a way to label that specific permutation. Now, if I square this, when you write it out, it's going to be 1/4. You will obviously have 1 minus 2P12 plus P12 squared. So what's your feeling about P12 squared? What should that be? So I interchange 2 and 1, yeah? Yeah, you're just back again, right? So this is 1, and now you see you have 2 minus 2P1. So this is just simply 1/2 of 1 minus P12, and that's equal to A2 here. And you can proceed in a similar way with 3 particles, 4 particles, and you can do the proof by induction. So that's a pretty standard procedure for showing that. So it's an idempotent operator. It also has the property that it is a Hermitian operator. So this is also an important property of that operator. Now I'm going to state something here, which is very important. And this is something you can prove because it follows from the fact that we have identical particles and indistinguishable particles. And one of the assumptions we have made about the Hamiltonian is that when you calculate an expectation value of the Hamiltonian, then you cannot tell, or that expectation value is the same if you interchange particle 1 and 2. Also because the Hamiltonian in general has specific symmetries, which means that you will get the same expression if you interchange the two particles. This is a property we have been using. We used also last time. This is something I will state without proofs. It means that this operator A with H0 commutes, because when you know that when you write a commutator, this is the same as saying that it acts on a specific state. So it commutes with, I have to bring back hats. It commutes with all parts of the Hamiltonian, all the single parts, and it commutes obviously with the full Hamiltonian. So I'm just stating this without a proof. So this is identically equal to 0. Okay. So this is a very important property of this operator. So I introduced this anti-symmetrization operator, and we are going to use that one now in setting up the wave function. So let me now rewrite the ansatz or the Slater determinant for this 1, 2, up to n. So I'm not using this more compact notation. Now, this was a Slater determinant which had a factor 1 over the square root of n factorial. But since I'm introducing this operator, I have to bring in an n factorial. I have my operator, which then expresses the way we set up the Slater determinant. And this is now multiplied with something which I will call the Hartree function. So this has a name in the literature, so it's called the Hartree function. And this function, h here, is nothing but the product of the single particle states. So it represents a specific ordering for the single particle state. So if we write this out in all detail, this is phi alpha 1, x1, phi alpha 2, x2, all the way up to phi alpha n. So we are occupying now the lowest lying states of the single particle basis. And we are filling them up with particles, and we are using that as an ansatz for the ground state of the system. Now, if you look back at this one, this is reminiscent of what we set up as A11, A22, A33, etc. So these are the diagonal elements of the determinant. But they also represent the way we are thinking of the physical basis, in the sense that if you now look back at this figure, which we had here, so we are starting with the first state, this one, then the second one, and then we proceed till we have filled in all the n slots. So what we are doing then is to find a specific ordering. And this is obvious because you don't want to keep track of all the possible ways you can order a determinant, because every one of these arrangements which you have, like these ones, so for a 3 by 3 determinant, you have 6 possible arrangements. And we would call these arrangements for configurations. Now, you don't want to save 6 configurations. You save only one. And then you have these operators which bring you to the other ones. So we're going to have a kind of ground way of representing a specific state. And we know then that by acting on that specific arrangement with this operator, we are getting all the other possible arrangements. Now, there's one additional thing I want to bring in from combinatorics, And that is, if we go back to this figure here, we are going to have n single particle states. So I will often label this as little n. This is a number which is larger or equal than the total number of particles. So if I have n such slots here and little n slots, then the total number of arrangements, which is also called configurations. That's the way we configure the system. So when I say configuration, that is a kind of jargon which I will use later on in the course. So configuration interaction theory, which means you setting up a Hamiltonian matrix to diagonalize, is based on you having set up all the ways you can configure your system. And this is simply given by n factorial divided by n minus n factorial multiplied with n factorial, just a binomial factor. And that just follows from the combinatorics that you can only have one particle in one slot. And when you reshuffle them in n little n slots, this is the number of arrangements you can make. So doing this in terms of some basic arrangement is something which allows you to store the information in one specific way, which saves space. And then you get the other ones by acting with these different operators. Now, the thing which I promised you, and I'm just going to anticipate this before we take a break, is that this operator which we have here is going to make life easier when we calculate expectation values and transition probabilities. So when I say expectation value, that is you calculating a quantum mechanical quantity where you go from one state to the same state. Typically, you would calculate the expectation value of the energy. If you go from the ground state to an excited state, this is a transition to a specific state. And normally we call that transitions or just transition probabilities, depending on what kind of operator you have. So when I say an expectation value, it's from the same state to the same state. Later, we're going to use that notation we introduced last time, where we simply call this for matrix elements, because we're going to store everything as matrices. Okay, so this is the kind of jargon I'm just bringing back and again. So after the break, we are now going to use this and calculate an expectation value. Okay, let's do 15 minutes of leg stretching or whatever you want to do. Probably you have tons of questions as well. Huh? So what we are going to do now is simply to calculate now the expectation values, but for more a general Slater determinant or a determinant. And the reason we want to do that is simply because a system of two particles is not that interesting. I mean, we can, for some type of Hamiltonians, we can even find analytical solutions for two-particle problem. So the many-particle problem is the one which is more interesting for us. So let's now look at how we can calculate an expectation value. So what we want now is with this specific ansatz, we want now to calculate the quantum mechanical expectation value of the full Hamiltonian. So remember now that we are writing this out in terms of an expectation value as the integrals, because our basis which we have chosen is not an eigenbasis of H. Okay? But we can make a linear combination of many such determinants within a single particle basis and then express the exact wave function in terms of that. That's something which is going to lead us to full configuration interaction theory later in this course. But so what we are going to do now is to get an approximation to the ground state. In atomic physics, if we use these hydrogen-like orbitals, this provides actually a pretty good ansatz to the energy of a physical system like atomic neon, atomic sodium, etc., etc. So it's actually pretty good. And that means that you need just to labor a little bit more to get closer and closer to the experimental value. So in other fields, if you're looking at strongly interacting systems like a gas or a liquid of helium-3, this is not going to work with a single particle basis. But let's go through the calculations of these expectation values. And now we're going to take the first term, H0 of phi 0. So in our case, this is now an integral. And since phi 0 is based on orthogonal and normalized functions, then the norm phi 0 is equal to 1 by construction. Because in principle, this guy here is actually given by the integrals, where we have H0, phi 0, but we have already taken and normalized the function phi 0. So this function here is by construction equal to 1. Because we're using an orthogonal and normalized basis. Actually, this is one of the exercises which you have to do, I think it's next week. Okay, so what we need now is just to introduce some kind of shorthands. So d tau is dx1, all is integral dx2 up to dxn. And this means that also just keep in mind that dx is actually given by a sum over the spin degrees of freedom and an integral over the spatial degrees of freedom. So we are going to stick with this kind of compact notation. Sorry, when I write dx like this, sorry. Okay, so what we do now is simply to rewrite this integral using this anti-symmetrization function, phi 0. So this is going to be equal now to an integral over d tau, and then we have phi 0. And now I'm just going to use this more compact notation with 1, 2, up to n. Then I have my h0, and then I have my phi 0, of 1, 2, up to n. Which again, when I now introduce this anti-symmetrization operator, is going to be given by n factorial. I have my d tau, and now I have my phi h complex conjugate. This is the Hartree function we defined before the break, which is just a product of the single particle wave function. So this is obviously a function which does not respect the symmetry, in the sense that if you were to calculate an expectation value here, you will not get the correct expectation value because it's neither antisymmetric nor symmetric. Then I have now the single particle operators, which I express with this. So A is Hermitian. This is the anti-symmetrization operator. And now I have this sum from I equal 1 up to n. And then I have this h0 of x of I. So this is my h0. And then I have my operator A acting on this phi of h. And I'm skipping the coordinates 1, 2, up to n, okay? Just to make things a little bit simpler. So I'm not baking in the equations now all these different variables. I hope you can forgive me for that. Now, if we now remember that this operator A commutes with h0, and that a squared is equal to a, you see now that I can rewrite this in terms of n factorial and an integral over d tau, and then I have phi of h complex conjugate times this h0 times a times phi of h, this Hartree product. So this simplifies a lot the calculations. Now what happens next is that I can now introduce this specific operator which I have. So I should put back the hats here, but sometimes I forget to put hats on. Like that. So what I do now is simply to introduce this operator A, which we then defined, if we now scroll back a little bit, we defined it like this. So there's a factor 1 over n factorial, and that is going to cancel this n factorial. So when I write it out now, this is going to be equal to d tau phi of h, which is just a product of single particle wave functions. And then I have my sum over the single particle guys, but let's just write it out like h0 first. And now I have a sum over all the possible permutations which I can make. So Sn is just a group of all possible permutations I can make with this number of particles. And then I have pi here, and then I have this permutation operator acting on phi h. So now we can start looking at all the possible permutations. So if we now take the first case, 0 permutations. And now let's write out what we get. So we are going to have now integrals dx1, dx2, up to dxn. And then I have this states phi alpha 1, complex conjugate x1. So when you see all this writing, you may ask, I mean, where's the simplification here, which I promised? We are going to simplify this further when we introduce second quantization. But now you will see the benefit of actually having introduced this operator. And here we're going to have now xn. And then there is a sum of h0, x1, plus h0, x2, and all the way up to the final one of xn, like that. And this is now multiplied with 0 permutations. So that means it has to be multiplied with phi alpha 1, x1, phi alpha 2, x2, etc., all the way up to phi alpha n of xn. So this was the case with 0 permutations. Now, if you now look at this, what you see now is the following. So let's just try to match things here. So if I take x1, obviously then I have phi alpha 1 and phi alpha 1 here. And if you pick one term here, where you have this one acting on that state, you see this is a sum. So each one of them acts on x1, x2, up to xn. So if we now single out this piece, if we take the first term, so we're going to have a dx1, and then we have a phi alpha 1, x1, h0, x1, phi alpha 1, x1, and then there's a series of integrals over dx2, and then I simply have phi alpha 2, x2, phi alpha 2, x2 here, and this continues all the way up to dxn of phi alpha n, xn of phi alpha n, xn. And in this specific case, we know that this one is equal to epsilon. Let me just epsilon alpha 1 times phi alpha 1 of x1. So the first term we looked at with this here picks out x1, and it simply produces this result here. And all the other ones, since the functions are normalized and orthogonal, that gives us just 1. So the first term gives us epsilon alpha 1. Then it's pretty obvious that I don't need to write down what happens with x2, x3, and so on. So this term here actually gives us, when we collect everything, it gives us a sum from I equal 1 up to n of epsilon alpha I. So that's a collection of single particle energies. Let's now look at the possible exchanges, right? So now we have the 0 permutations. Now we take 1 permutation. And let's suppose now that we interchange column 1 and 2. So we interchange particle 1 and 2. So that means that we are going to get, so we now interchange 1 and 2. So particles 1 and 2. That means that we are going to have an integral here, dx1. So let's just write it down, and then we have dx2. And then we have all the other ones up to dxn. And we have phi alpha 1. So this is left unchanged. Phi alpha 2, x2 here. And then we have all the other ones up to phi alpha n of xn. And then we have h0, x1 plus h0, x2, etc., up to the final value. And this is now multiplied with phi alpha 1, but now I have x2 here. And phi alpha 2 of x1 and phi alpha n of xn. So if you now start looking at it, we have an integral, a normalization integral with dx2, which involves alpha 2 and alpha 1. But then we have another integral with dx1, which involves this one, that one, and this one. And alpha 1 is different from alpha 2. So that means that one permutation or any other permutation is going to give us 0 due to the orthogonality. Okay? It's pretty easy to see that this is also what would happen if you interchange any other particle, because you will have this order here, which is unchanged. But if I make one or more permutations, I will always have a guy here which has a different quantum number from the one here. So that means that one or higher permutations is going to give us 0. Can you see that intuitively? Because if you make one or two permutations, you will always have orthogonalization integrals which are different, which have different quantum numbers. So that means that the result which you see here, so this is obviously going to be equal to 0. So the only plus all other permutations. All other permutations or transpositions is a better word. So the final result for that expectation value is this one. So you see now that compared to the case which we did last week, where we did the Slater determinant for two particles, we had to go through all the integrals. Now we can actually easily set it up in terms of a term here which is unchanged due to this anti-symmetrization operator, and then a term which is given by the different types of permutations we can make. So this is the first part. So let's now move to the second part. So the second term we need to calculate is actually this guy here with the interaction, I for the interaction piece. Now again, the norm of phi 0 is equal to 1 by construction. So this is going to be equal to this n factorial, and then I have a d tau, and then I have this R3 function, and I'm skipping all the coordinates of the particles. And then I have the anti-symmetrization guy, which is Hermitian. And then I have h of I multiplied with a times, so this is an operator, 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 and phi of h. And again, we know that the h of I commutes with this one. So this is the same as h of I, just to remind you of that, times a times h of I. This is 0. So I can rewrite this integral now as n factorial of d tau, and then I have phi of h, and then I have h of I multiplied with a, because a squared is equal to a, multiplied with phi of h. So I'm back to the same thing which I had previously, except that now this operator acts on two particles at a time. The previous one acted only on one particle at a time, because now we have a two-body operator. So if I now write this out and I plug in the definition of A, this is going to be equal to d of tau of phi h of h of I. And then we have this sum over all the permutations times this operator P multiplied with phi of h. So let's write it out now and see what we get, okay? So in full glory, this is now going to be a sum over the interaction elements. So I have ij. I have an integral over dx1, and then I'm getting up to dxi. There's going to be a dxj, and then I have a dxn. And this is now multiplied with a phi I, a phi of x1, a phi alpha 2 of x2 complex conjugate. There's going to be a phi alpha I of xi. And then somewhere there's a j, alpha j of xj. And this is given by the last one, complex conjugate xn. And then I have an interaction element which picks coordinates x and j. And this is now multiplied with the different transpositions I can make. So I would now have this sum over p of pi, I call it pi, of Sn minus pi, and then I have this operator, and this is multiplied by phi alpha 1, x1, and then I have my phi alpha I, not complex conjugate, xi, alpha n, and xn. And now I can pick the different terms, okay? So let's now pick the term p equals 0, no permutations. And I'm just going to look at an integral which involves xi and xj. So if I do that, that means that there will be integrals over dx1 with this one, and only that one, which will simply give us 1. And similar, there will be a dx2 up to dxn, except for these two, which will all give us 1. So the only thing which survives here when I take this sum over ij here is actually something which goes like the sum over I less than j, and the only integrals I need to evaluate is dxi, because all the other ones just give us 1, because these are normalized single particle states. So I'm going to have a phi alpha I, alpha a, xi, phi alpha j of xj, multiplied with v of xi, xj, and then I have phi alpha I of phi alpha j of xj. This is what we last time called a direct term. There is no interchange of particles here, okay? Okay, so if we do that, then we are going to use a shorthand here. Remember that last time we actually called this integral, we gave this integral a shorthand term in terms of the Dirac bracket notation. And so we simply wrote this integral as an alpha I, alpha j of v, alpha I, and alpha j. So the way you can think of this is that particle 1 is in that slot, and particle 2 is in that slot. And the same here. And you see that immediately here that particle 1 is in xi, and the first one is in xi, and the second one is in xj. So you can think of that as specific slots for the particles, which are placing in specific quantum numbers. So this is a kind of shorthand for the integral which you see here. And obviously we have to keep the sum because we pick 2 and 2 particles at a time. And all the other integrals are equal to 1. So let's now make one interchange. So we just interchange I and j, okay? So we take now p equal to 1. And in this specific case, it's only I interchange with j. Then we need a minus sign. So we get a minus. And all the other integrals are equal to 1 over dx1, dx2, dx3, except for xi and xj, because they are being treated by the interaction. So we don't know whether this term is 0 or not. So it could actually be 0 for many types of interactions, but we don't know that. So here we would get the same sum over I and j, and then I have a dxi, and then a sum integral over dxj. And the left-hand side is left unchanged because we don't have an anti-symmetrization operator acting on it. So this is always, it keeps always the same order of xj. And this is then multiplied with v of xi of xj, the comma here. But now I have interchanged. So in alpha I have xj, and in alpha j, I have xi. So this is also not necessarily equal to 0. So we have to keep it. It could happen that the spins are arranged so that it becomes 0. But in general, we have to keep it. And this is normally called the exchange term. And this is due for fermions, it's due to the Pauli principle. And we labeled this one last time as an alpha I, alpha j. Oh, sorry, there's a j here. And a v alpha j, alpha I. So if you still insist on the ordering that this is the first particle and this is the second one, you see now that we have interchanged the quantum numbers, as you can see in this expression here. Because now xj has been flipped with xi. So this is just more a compact notation which we are going to get. Now, this is the case where we have I and j. Now, if I now make any other type of permutation, and I leave that as a small exercise to you guys, any other permutation is going to give us 0. So suppose now that instead of I and j here, I pick a number k here. If I do that, then the number k here will actually have quantum numbers where I will have one of the one-body integrals or the normalization integrals, which will be 0. And you can see that easily. So any other permutation than the 0 permutation and this permutation where you just interchanged those two elements which are acted by the interaction, these are the only non-zero terms. And you can see that if you now try to permute or interchange some of the other columns, because the interaction acts only on I and j. So one thing you could do now is to just take particles 1 and 2, just write 1 and 2 there. And then if you now interchange 1 and 3, then that will give you 0, because you will have an integral which now contains a quantum number which is different from the one when you integrate over x2 and x3, etc. So it's pretty easy to see that. So it means that the final result, which we are going to get, so I'm just going to write all other permutations, except those which belong to the quantum numbers or the coordinates of the interaction are 0. So sometimes it's actually useful to write out the 3x3 case, and then you will see it immediately. So if I'd had a free body interaction, then I could actually interchange the columns and rows for, no, the columns for free particles. And then, because the interaction would then act at 3 at a time. But then if I went beyond interchanging just 3 objects, and I did interchange 4, then that would give me 0. So a free body interaction gives us additional terms, which then would respect the write out of a determinant, a 3x3 determinant, which has 6 terms. So a 3x3 determinant would then give you 6 such integrals, because you have the 3 factorial ways of writing out the arrangement of these states which you see here. So you see now that with 2, you have only 2 possible integrals. With a free body interaction, you would actually get 6 contributions. But if I have a free particle state and I have a 2-body interaction only, then there will be integrals for the single particle wave functions, which will be 0. So as a small exercise, try this out for a 3x3 determinant. And then you will see that if you have a 2-body interaction, it's only this permutation here which survives. So with 3 particles, you can change 1 and 2. You can change 1 and 3, and 2 and 3. But if you change 1, 2, and 3, you make that change, then that will give you 0 with a 2-body interaction. So this is something which sometimes it's useful to do by hand yourself. Okay, so that means that if I collect everything, I'm going to get the following expectation value. So this is something which we often write like this. We have an H0 acting on alpha I. And since this is a basis, which is an eigenbasis of H0, this becomes equal to epsilon alpha I. And this is the energy. This is actually what you get here. This is something which we would simply label as H0, which is the eigenenergy of H0 acting on phi 0. So phi 0 is an eigenbasis for H0 by construction. And then we have the additional term here. And now I'm going to write this out in a more compact way. So we have I less than j. And I'm going to remind you of those integrals which we defined last time, which are given in terms of what we call anti-symmetrized matrix elements. So this is alpha I, alpha j. Now let me try to squeeze it in better here. Let me just cancel it here. Let's just do it like this. So let me put it in here. Hopefully I have more space. So this has an alpha I, alpha j, v, alpha I, alpha j, minus alpha I, alpha j, v, alpha j, alpha I, like that. Now, this is something which we can write in an even more compact way in terms of these anti-symmetrized matrix elements which we defined last time. So last time, what we did was to lump together this direct term and the exchange term into one matrix element, which we call anti-symmetrized. So let me just bring that back from last time. So we defined something like Ij, now I'm just writing this generally, Kl. So these are different quantum numbers. Anti-symmetrized is given in terms of the direct term of V of Kl minus, so these are integrals, LK. It has the symmetry property, which you can easily deduce, anti-symmetrized, and that's equal to JI V of LK, anti-symmetrized, which is again equal to minus JI V KL, anti-symmetrized. And I can also interchange L and K and just leave I and J in the specific place. So this is just a kind of compact notation which we will use throughout the course. So in many applications of many-body methods, this is very convenient because then you just have one element you would look up in a table. And then you have pre-calculated the two integrals. If you're calculating the integrals on the fly, which is often the case in atomic and molecular physics, where you can use properties of the Coulomb interaction, then you would actually have to calculate the integrals. But you have sometimes tables of these integrals which become too large to store, because then you spend a lot of time in searching in a table. Whereas if you can calculate on the fly, sometimes it can be cheaper from a computational point of view. So that depends, it's something which varies from case to case. So I can then rewrite this expectation n value So I would have this epsilon 0, which is what we will call the non-interacting total energy, plus, and if you look back now to the expression down here, we have a sum where I is less than j, but you could sum freely. And if you sum freely, then you have to, due to the anti-symmetry and the properties of these integrals, they are symmetries, you can actually rewrite this one like a half. And you know that when I is equal to j, the two terms cancel each other. And then you don't want to double count because you get the same contribution when you have j less than I or I larger than j, no, I less than j. So I would write this out like this, anti-symmetrized. That's the compact way of writing this expression. Now we can do further manipulations, but I'm going to leave some of them till later. The thing which now is going to be interesting for us is, we can ask the question, can we simplify this machinery even more? And that is where second quantization or the number representation comes into play. So everything we did here is done in a full representation with all the quantum numbers. And normally we call this the coordinate space representation because we keep track of all the quantum numbers. We have the spin degrees of freedom, the spatial degrees of freedom, and we then write out all the integrals here. Now the question is, can we introduce a formalism where we have integrated away the spatial degrees of freedom and the spin degrees of freedom, so that at the end, we are simply fetching elements here from a table or have an algorithm to calculate them on the fly. Now, this is where second quantization comes in. And the way you can think of that is a mapping of your Slater determinant, which has all the degrees of freedom, to a new space where you only keep track of which single particle states are occupied or not. Okay? This is a kind of motivation. So we are always, as humans, we are always looking after simplifications, ways by which we can extract the same information in a simpler way. So that's a kind of motivation for second quantization, which is an extremely powerful way of expressing complicated states and the expectation values of a given operator or transition probabilities. Any questions so far? So I'm going to bring in the definitions, and tomorrow we are going to derive specific anti-commutation rules for these operators. So the expressions we have found are expressions which are extremely useful, but you saw that we needed quite some labor to find the expectation values. So the question now is, can we do something simpler? And now I'm going to introduce the number representation. Or second quantization. So I'm not going to bring in any mathematics of it now, but I wanted to give you a kind of motivation for how we think. So what we have done is to pick a single particle basis. And with that basis, we construct a many-body basis. So we have some states, which we just label as 1, 2, 3, and then we are filling in these slots with particles up to n. So there is a basis which now is ordered according to ascending energies. So we could have now the lowest lying state epsilon 1, then we have epsilon 2, epsilon 3, etc., up to epsilon n. And then we decided to call this, if we have fermions, we would typically call this for the Fermi level. And then we have further states up here. So we have an epsilon n plus 1. So these are single particle states, n plus 1. And this goes all the way to infinity. But as I said, we are going to truncate. Now, the states which we have, we are going to label them in a specific way now. But let's now think of us putting in, suppose now that we have n equal to 2 here, and we have little n, the number of slots equal to 4. So I have now the number of possibilities is actually given by 4 factorial divided by 2, divided by 2, and that's 2 factorial, and that is actually 6 possible arrangements I can make. And let's just call these for given slots or boxes. And now we're just looking at 4 such boxes. Now, one way to organize the state now is that we think of these as arrays. And we could have an arrangement where this one is filled. This is 1, 2, 3, 4. And the other ones are empty. If we now have a bit representation, you can think of 1 as occupied and 0 as empty. So you could actually, if you want to make a bit representation of this state, you could now think of the first bit for box 1, the second bit for box 2, so that's a bit 1, and 0, 0. So that could be a compact way, so you have 4 bits, which you use to represent a 2-particle state. And you could now just rewrite this in a bracket notation, so this will be your representation. So the second quantization formalism is actually something which, from a computational point of view, leads to a very compact and efficient way to represent states in a computer, because you can actually use Boolean algebra. So this is something which makes it very efficient to program fermionic systems. So if I have another example, I could now take this example here, and then the other ones are empty. So this would translate into 1, 0, 1, 0. And that gives us a state 1, 0, 1, 0. So that could be a way to represent that state. Now, when you have enumerated all these possibilities, you have only 6 possibilities. So that means you need to store 6 numbers. So you could find a simple recipe where you then label them in an ascending order, like state 0, state 1, state 2, state 3, 4, and 5. And you can actually use the bits here to reconstruct from that string of bits. You could then reconstruct a number which is stored in memory. So this is a kind of starting point for the second quantization formalism. And tomorrow we're going to look at the introduction of specific ways by which we can now fill in these boxes. So we are going to define something which we are going to call the true vacuum. So that's 0. So that's just emptiness. Sounds like my brain. after the lecture. And then we are going to have operators which act on this state and adds or subtracts a particle from that specific state. And these are going to be creation and annihilation or just destruction operators. We normally call them creation and annihilation because destruction sounds a little bit, not so nice. So we are going to introduce tomorrow specific operators which act on these slots and either create or remove a particle. So that means that we are going to introduce a language where we're going to interpret physical states as excitations around the Fermi level. So when you kick out a particle from here and up here, that leaves a hole below the Fermi level, and you have a particle above it. And in the many-body jargon, this is called a one-particle, one-hole excitation. That is a new Slater determinant. You have the same number of particles, but you have simply, through some physical process, you have excited a single particle state to another single particle state. And that leaves a spot below the Fermi level. But this is still another Slater determinant. So we are going to construct a basis, a many-body basis in terms of these creation and annihilation operators. And it's going to introduce a language where we interpret physical processes in terms of what we are going to call particle excitations, particle hole excitations, etc. So this gives a very handy way to interpret physical states. And keep in mind then that we have removed the spatial degrees of freedom because they will be baked into integrals, which are just stored, and you can fetch them when you have the indices, because this will be index for state 1, this for state 2, 3, and 4. So when you need to fetch an integral, you simply transfer these indices, and then you know exactly what that integral is because you have stored it somewhere, or you can calculate it on the fly. So this is a kind of overarching entry points to the technicalities of tomorrow. And these technicalities are also in the slides for this specific week. Okay. So the motivation is to find a more compact way to represent physical properties. And it's also a very elegant way of doing it. Yes, that's my prejudice. Okay. Okay, I'm going to stop the recording.